Hi everyone and welcome to this lecture. So we are going to start discussing series solution of ordinary differential equations, and today we are going to talk about some prerequisites that will be essential for the series solution concept. So the series solution comes because most of the differential equations are not solvable in analytical methods, because we have seen some examples that are really simple and that are doable, where differential equations are notoriously difficult to solve, and most of the time there is no analytical solution at all. And even through this series solution sometimes doesn't yield any analytical solution, but it can give some good approximation. And what one does at that point is that either they refer to the series solution or a numerical method that provides some approximate solutions. So let us start, and we're going to start with some prerequisites. So prerequisites, and the first prerequisite is to know that what is a power series. That means we need to know about power series. And the definition for this power series is that if you have a series like this, this is called a power series. And let me now explain the terms. This n is called the coefficient. This t is called the independent variable. T0 is again a real number, and obviously the coefficient is also a real number, so this also belongs to R. And this n is the number of iterations. So if you expand this expression, let's call it expression 1. So if you expand this will look something like a0, a1 t minus t0, a2 t minus t0 square, and so on. So this is an example of a power series, and this power series is said to be expanded around this point t0. So that's why the t0 thing comes here. And a very familiar example that you all know already is that something called a Taylor expansion of a function, or a Maclaurin expansion. Maclaurin expansion is just a special case of Taylor expansion where the reference or where the point of interest is just 0. So this Taylor expansion of a function, let's say f of t, can be written as n equals to 0 to infinity f of n, which is just the n derivative evaluated at point 0, t0, and there's this n factorial thing, and you have t minus t0 over n. And if you compare, let's call this equation 2, and if you compare equation 1 and 2, this is not going, so let's try to get rid of this. So if you compare equation 1 and 2, that is this one over here and this one, you can easily see that n is just f of n t0 divided by n factorial. Obviously this f of n, again I'm just reminding you, it means the n derivative of function f, and then you are evaluating at point t is equals to t0. So these are the power series stuff, and this is all you need to know about power series, that how to write them, how to distinguish different terms. These are all the things you need to know about power series. And next thing, the next prerequisite that we are going to discuss today is something called analytical function. By analyticity, let's call it analyticity, not analytical, because that would that's actually quite a misuse of the term analytic function, because it's a matter of great care that is taken into only complex variable courses. But since we are not doing complex variables, we are only restricting ourselves with real numbers. So we want to discuss something called an analyticity of a function of real variables. Alright, so a very schematic definition, not the very formal definition, that is a very schematic definition for this analyticity of a function is that a function that is a differentiable function is analytic, or okay, let's just forget about the differentiability. Alright, so in simple terms, a function is analytic if the Taylor expansion converges for f of it at all points in t in some open interval, and within that interval that function is defined. So if I want to put it in words, analyticity means an analytic functions, and obviously please don't confuse with the complex variable cases, because that's the more formal definition, but we are only sticking with the informal definition here. And what for our purpose, analyticity means, let's say you have some open interval, something like this, let's say, and you have some function f of t. This is your function, and within this open interval a and b, let's say, the Taylor expansion will always converge. That means the Taylor expansion of f of t within this interval. If this condition is satisfied, then the function is called an analytical function. For our purpose only, obviously keep that in mind. So this is another useful prerequisite. And now obviously, if you remember, we'll since we are doing the series solution thing, we are going to restrict ourselves up to second order equations. Third order is also doable, but it's very lengthy. So that's why we will stick up to only second order equations. So if you recall, we were dealing with equations like this in our previous lectures, right? Second order equations where t is the independent variable, prime means the derivative, and obviously we can even do it for non-homogeneous equations as well, but let's stick with the homogeneous terms. So we will deal with this kind of equations, and if you write this in a standard form, that means you divide by p of t, you will get q of t, p of t, y prime, r t, p t, y equals to 0. This is the standard form. So I'm writing it as SF, that means standard form. So now, since this p of t is in the denominator, and because of this there comes the idea, and this is a prerequisite that will also be important. Since p of t is in the denominator, there might be points where p of t is not even defined, or there might be points where p of t is defined but the ratio q by p, it's not defined. But since you are only seeing a ratio over here, we actually care about the ratio itself, these ratios. So based on this thing, there comes the idea of a singular point. So singular points of a function. In short, these are points where the function blows up. This means, let's say you are considering a function f of x, and this function has this form x minus 1. So if you try to put f of 1, you can see there's a 1 by 0. Obviously you write it something like this, infinity, but that's not correct. it's not infinity, it's blowing up. This means as you approach 0, the value for the function goes higher and higher and higher and higher. A very schematic graph will look something like this. If this is the origin, this is point 1, let's give a dot 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 dot, and this is how the function's curve should look, if I'm not mistaken. That is this one. And as you can see, this is, if this is 1, this is indeed 1, and if you approach 1, you can see that the value of the function is getting higher and higher and higher and higher. So that's what we mean by blow up. It blows up. Nobody knows what happens. So since we care about the ratio, Q by P and R by P, we can see that we can make these ratios blow up by setting P of t equals to 0. So we can blow up these ratios using, oops, sorry about that. Oh, not again. Yeah. So we can blow up these ratios using or making P of t to be 0. So these points where the functions blows up, so points where functions blow up are known as singular points. And this, whenever this P of t is 0, that should indicate towards some singular points. And this will also help us, that is this condition, P of t is 0, this will be the key to identify the singular points. And this definition that I gave you here, that's an informal definition, but it gives you the idea or the motivation about singular points. And how a solution of a differential equation will look will depend on whether we are trying to see it from a regular point of view, that is whether we are trying to find a solution around a regular point or a singular point. So this also brings up the idea of the regular points. So regular points are also important, and any point that is not singular, those are called regular points of a function. So at that point it has some finite value, something that we can make sense of. So this regular points, any point that is not singular. Obviously your function has to be defined on that point. Let's say you are taking some point and that point lies outside the interval on which the function is defined. That really doesn't count because the function itself is not defined there, so you cannot comment anything. So this means any point that is not singular. And finally we are going to see two more definitions, and this will be about singular points as well. So these two definitions are called the regular and the irregular singular points. So singular points are two kinds. One is a regular singular point, regular singular point. Another one is called irregular singular point. So let us discuss this regular singular point first. So regular singular point. So since we are dealing with the differential equations where there is some ratio like q by p and r by p, the definition of a regular singular point is that if you have some point t0, this is some point, and you are seeing that for this t0, p of t0 equals to 0, but this limit when t goes to t0 for t minus t0 times the ratio q of t by p of t is less than infinity. If you see this thing is happening, and at the same time you see that limit when t goes to t0, t minus t naught squared r of t p of t is less than infinity, then this t0 is called a regular singular point. Alright, and this is the formal definition of a regular singular point, and this means that even though p of t naught, that means the function p of t at point t0 is 0, it's just analytic. That means at the regular singular points, the functions themselves are analytic. That's what it means. And obviously you might ask, what is I'm discussing so much about the singular point, so what is the physical significance of the singular points? So let me just write a few words about it. So singular points from a physical or application point of view, it indicates phenomena with a certain lack of smoothness. Phenomena with certain lack of smoothness. That's what the physical interpretation of these singular points are. And whenever you are asked that whether a point is a regular singular point or an irregular singular point, if you want to check that whether it's a regular singular point, you have to take both of these definitions. That means they have to be satisfied simultaneously. So this is an important fact to keep in your mind, that the kind of differential equations that we are dealing with, if they have some singular points and you are asked to find whether the singular points are regular, you have to show that both of these are true. And any point that is not a regular singular point is called an irregular singular point. So irregular singular points are those who doesn't satisfy these conditions over here. So let's call these conditions as A. That means these two conditions. So who doesn't satisfy conditions in A? That is the expression. And now it will be nice if we can see an example. So obviously I'm going to show an example, so let's call this example, and this example will be for this singular points and regular and irregular singular points. So the example that we are going to consider today is pretty simple. Let's say you have a differential equation like this, t, then t plus 1 whole square y double prime plus t plus 2 y prime plus 2t y equals to 0. Now let's bring this thing into a standard form. So the standard form is nothing but y double prime plus t plus 2 t into t plus 1, 2t. This t and this t will cancel each other out, so this is just t plus 1 squared y equals to 0. Now in the previous part I discussed about this q and p and r, but notice that I also told you that the ratio is the only thing that matters, the only thing that we care. So this is the thing we should care. And to find the singular points, we just look at the denominator and we find out for which points this part, that means this this denominator and this denominator, they're 0. Obviously you can also go with the pq part as well. It won't hurt if you do that. So if you just make this t of t plus 1 equals to 0, this gives you t equals to either 0 or t equals to minus 1. And similarly for here, you will get t equals to minus 1 if you consider this to be 0. Obviously we are not considering the multiplicity and all that. So now we want to see whether these singular points over here, that means these are our singular points, and now we want to see whether they are irregular or regular. So to do that, first go with the condition. Let's say we want to check for t equals to 0, right? So if you recall, this t naught will now be 0 because we want to test for this t naught. So we write limit t goes to 0, and this will be t minus 0, and obviously qt by pt, this thing. Then we use the values of q and p that we can see from here, this part. So this q is nothing but t into t plus 2. Obviously this t is coming from just there, and here in q you can see that there is no t. So this t over here, that is over here, is coming from t minus 0. So that's why I have written it as t into t minus 2 divided by p. P itself is t into t plus 1 squared. And now we're saying what's the limit when t goes to 0. And this is pretty easy, right? You'll have something like this, and limit t goes to 0. And if you evaluate the limit, this is just 2, which is less than infinity. So that's good. And now there was another condition, and for that condition you have to do t goes to 0 and you write t minus 0 whole squared, and our r was simply 2t. So, and p was just t into t plus 1 whole square. So t into t plus 1 whole square. So yeah, this is just the r of t by p of t ratio. So now if you do the algebra, this will just be 2t squared by t plus 1. Obviously one of the t's will get cancelled, and you will have limit t goes to 0, 2t, t plus 1. Yeah, the t should be like this, so that we can distinguish it from the summation symbol, sum symbol, or whatever, addition symbol. And now if you evaluate the limit, this is just 0, which is also less than infinity. Since both of the criteria have been satisfied, we can say that 0 is a regular singular point. Though it's singular, but it's a regular singular point. So you can find some series solution about this point as well. Now let's go for minus 1. So checking whether -1 is a regular singular point, that means RSP, or irregular singular point, ISP. So again, we are going to use the same thing. We say t goes to -1, you write t minus -1, and here you should have right now as the q. So the q was simply t plus 2, and the p was simply t into t plus 1 whole square. And in the next line you write t goes to -1, so this is just t plus 1. So this is t plus 1, t plus 2 divided by t plus 1 whole squared. You do the algebra and you evaluate the limit. That's as simple as that. So this is just 2 plus t plus 2, this is t plus 1. Now if you evaluate the limit, you can easily see that this is infinity, which is not less than infinity. So even if one of the conditions in the two conditions you saw in expression A, so let me get back to that and make an important comment. So even if one of the conditions gets violated, the point is not a singular point, regular singular point. So you are checking these two conditions, and if one of them is getting violated, that's it. That's not a regular singular point. But to be a regular singular point, both of them have to be satisfied. And yeah, this is all for today. And and these are all the prerequisites. Oops, sorry about that. Yeah, now that looks good. Okay, this is good. So yeah, as I was saying, so this is it for today, and all of these things that you saw in today's video, they will be useful when we try to construct the solutions of differential equations using power series. So this will be it for today, and thank you.